Let's now discuss about combinational circuits. Combinational logic circuit is a type of digital logic which is implemented by the Boolean circuits, where the output is a pure function of the present input only. Combinational circuits do not have any memory devices. Combinational digital logic circuits are basically made up of digital logic gates like AND gate, OR gate, NOT gate, and the other universal gates. All these gates are combined together to form a complicated switching circuit. The logic gates are building blocks of the combinational logic circuits. A combinational circuit consists of input variables, we can call it as N, logic gates, and output variables, we can call it as M. For N input variables, there are 2 power N possible combinations of binary input values. For each possible input combination, there is one and only one possible output combination. A combination circuit can be described by M, Boolean functions, one for each output variable. Each output function expressed in terms of the N input variables. 3 main ways of specifying the function of a combinational logic circuits are: the first one is Boolean algebra. This forms the algebraic expression showing the operation of the logic circuit for each input variable, either true or false, that results in a logic 1 output. The second one is the truth table. A truth table defines the function of a logic gate by providing a concise list that shows all the output states in the tabular form for each possible combination of input variable that the gate could encounter. The third one is your logic diagram. This is a graphical representation of a logic circuit that shows the wiring and the connections of each individual logic gate, which is represented by a specific graphical symbol that implements the logic circuit. As the combinational logic circuits are made up from individual logic gates only, they can also be considered as decision-making circuits, and combinational logic is about combining logic gates together to process 2 or more signals in order to produce at least one output signal according to the logical function of each logic gate. Common combinational circuits made up from individual logic gates that carry out a desired applications. It includes multiplexers, demultiplexers, encoders, decoders, half adders, and full adders, and many more. Moving forward, let's look into some of the examples of combinational circuits. Adders. An adder is a digital circuit that performs addition of numbers. In many computers and other kinds of processors, adders are used to calculate addresses, similar operations, and the table indices in the ALU, and also in other parts of the processors too. Digital computers perform a variety of information processing tasks. Among the basic functions encountered are the various arithmetic operations. Adders can be classified into 2 types: half adder, full adder. Half adder circuit has 2 inputs, A and B, which add 2 input digits and generate a carry and sum. The full adder circuit has 3 inputs, A, B, and C, which are the 3 input numbers and which generates the carry out and the sum. Let's look at half adder. Half adder is a combinational logic circuit with 2 inputs and 2 outputs. The half adder circuit is designed to add 2 single bit binary numbers A and B. It is a basic building block for addition of 2 single bit numbers. This circuit has 2 outputs, that is carry and sum. These are the least possible single bit combinations, that is 0 plus 0 is nothing but 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 1 0. But the result for 1 plus 1 is 1 0. The sum result must be rewritten as a 2-bit output. Thus, the equations can be written as the output 1 of 1 0 is carry out, sum is the normal output, and carry is the carry out. The figure shows the block diagram of the half adder along with its truth table. The half adder adds 2 binary digits called as augend and addend and produces 2 outputs as sum and carry. XOR is applied to both the inputs to produce the sum, and AND gate is applied to both the inputs to produce the carry. By using a half adder, you can design simple addition with the help of the logic gates. Now, it has been cleared that 1 bit adder can be easily implemented with the help of the XOR gate for the output sum and the AND gate for the carry output. When we need to add two 8-bit bytes together, we can be done with the help of a full adder logic. The half adder is useful when you want to add two binary digit quantities. A way to develop a two binary digit adders would be to make a truth table and to start reducing it. When you want to make a 3 binary digit adder, we can do it again. When you decide to make a 4-digit adder, we can make it again. The circuits would be faster, but development time is slow. Let's discuss about full adder. Full adder is developed to overcome the drawback of the half adder circuit. It can add two 1-bit numbers A and B and the carry 2. This adder is difficult to implement than a half adder. The difference between the half adder and the full adder is that the full adder has 3 inputs and 2 outputs, whereas the half adder has 2 inputs and 2 outputs. The first 2 inputs are A and B, and the third input is called as carry in, which is denoted as C in. With the truth table, the full adder logic can be implemented. We can see that the output S is an XOR between the input A and the half adder. The sum output with B and C in inputs. C out will only be true if any of the 2 inputs out of the 3 are high. So we can implement a full adder circuit with the help of 2 half adder circuits too. At first, the half adder will be used to add A and B to produce a partial sum, and a second adder logic can be used to add the carry in to the sum produced by the first half adder to get the final output S. If any of the half adder logic produces a carry, there will be an output carry. So C out will be an OR function of the first adder carry outputs. Let's see about 4-bit parallel binary adder. A single full adder performs the addition of two 1-bit numbers and an input carry. The parallel binary adder is a combinational circuit which consists of various full adders in parallel structure, so that when more than 1-bit numbers are to be added, then there can be full adder for every column for the addition. A parallel adder is a digit circuit which is capable of finding the arithmetic sum of the two binary numbers that is greater than 1 bit in length by operating on the corresponding pairs of bits in parallel. This consists of full adders which is connected in a chain where the output carry from each full adder is connected to the carry input of the next higher order full adder in the chain. An n-bit parallel adder requires n full adders to perform the operation. So, for the 2-bit number, 2 adders are needed, while for 4-bit numbers, 4 adders are needed, and so on. Parallel adders normally incorporate carry look-ahead logic to ensure that the carry propagation between the subsequent stages of the addition does not limit the addition speed. Let's look at the working of a parallel adder. As we can see, firstly the full adder FAA adds A0 and B0 along with the carry, that is Cin, to generate the sum S0, and the carry C1 which is connected to the next adder in the chain. Next, the full adder FAB uses this carry bit, that is Cin, to add with the input bits A1 and B1 to generate the sum S1 and carry C2, which is again further connected to the next adder in the chain, and so on. The process continues till the last full adder FAN uses the carry bit Cn minus 1 to add with its input An minus 1 and Bn minus 1 to generate the last bit of the output along with its carry bit Cout. Let's look at the advantages of a parallel adder. The advantage of using a parallel binary adder is its fast processing. It is certainly beneficial for the addition of the numbers with more than 1 bit. Apart from this, during the addition process, all the bits are fed to the input terminals of the adder simultaneously. Now, you can easily compare this process with the conventional addition process which we do with a pen and paper. But in that, we add one column at a time, and in this several columns can be added simultaneously. Now you can estimate the speed of addition with the help of parallel binary adder. It is extremely fast. The time required for addition does not depend on the number of bits. The output is in parallel form. That means all the bits are added at the same time. It is less expensive. Let's look at the disadvantages of the parallel adder. Each adder has to wait for the carry, which is to be generated from the previous adder in chain. The propagation delay, which is nothing but the delay associated with the travelling of the carry bit, is found to increase with the increase in the number of bits to be added. If parallel connected full adders can increase the speed of operation, then these parallel connected adders are also responsible for the increased complexity of the circuit. The higher the number of bits, the more will be the circuit complexity. Let's now look at subtractor. It is a basic electronic device which is used to perform subtraction of two binary numbers. In the earlier slides, we have already discussed the basic theory of half adder and full adder, which uses the binary digits for the computation. Likewise, the full subtractor uses binary digits 0, 1 for the subtraction. The circuit of full subtractor can be built with logic gates such as OR gate, XOR gate and the NAND gate. Subtractors can be classified into two types: half subtractor, full subtractor. Let's discuss about half subtractor. Half subtractor is a combination circuit with two inputs and two outputs. The two outputs are the difference and the borrow. It produces the difference between the two binary bits at the input and produces an output borrow to indicate if one has been borrowed. In the subtraction A minus B, A is called as the minuend bit and B is called as the subtrahend bit. The designing of an half subtractor can be done by using the logic gates like NAND gate and the XOR gates. In order to design this half subtractor circuit, we have to know the two concepts, namely the difference and the borrow. We can clearly see from the truth table that the variety of operation executed by this circuit is accurately related to the XOR gate operation. Therefore, we can simply use the XOR gate for making the difference. In the same way, the borrow produced by the half adder circuit can be simply attained by using blend of logic gates like AND gate and the NOT gate, or simply we can go ahead with a NAND gate. Full subtractor. Full subtractor is an electronic device or a logic circuit which performs subtraction of two binary digits. It is a combinational logic circuit which is used in digital electronics. The foremost disadvantage of the half subtractor is we can make a borrow bit in this subtractor, whereas in full subtractor design actually we can make a borrow bit in the circuit and can subtract with the remaining two inputs. Here A is the minuend, B is the subtrahend and Bn is the borrow in. The outputs are difference and B out, that is nothing but the borrow out.